Good afternoon, everybody. My name's David Miller. I'm the CEO of the Concrete Institute of Australia, and it's my great pleasure today to welcome you to our webinar, which is being hosted by our NEXGen committee. Today's webinar is titled Lowering Concrete's Carbon Footprint. As mentioned, it's hosted by our CIA NEXGen group, and in particular, this has been organised by two of our NEXGen steering committee members based in Victoria, including the chair of our NEXGen steering committee, Arun Arunathayan, and also Sachi Kurunaratharan, who is also based in Melbourne. Today's presentation is brought to you by, including two presentations from two of our NEXGen young professional members within the concrete industry. But before we get into the presentations, just a little bit about the Concrete Institute of Australia. Our vision is excellence in concrete, and our mission is to provide resources and opportunities for the promotion and the development of excellence in concrete research, technology, application, design, construction, and sustainability. And as always, we acknowledge the traditional custodians of country throughout Australia and their connections to land, sea, and community. And we pay our respect to elders past and present and extend that respect to all Aboriginal and Torres Strait Islanders peoples today. As I mentioned before, today's presentation is brought to you by our NEXGen steering committee. And NEXGen aims to promote the membership of aims to promote the membership of young professionals in the Concrete Institute of Australia and to encourage involvement within the organisation of events and conferences. And we just finished our conference in Adelaide last week, and it was a terrific event, and we had some fantastic interaction and contribution from our NEXGen community. And the NEXGen objectives are promoting collaboration, building networks and connections, exchanging knowledge and experiences, organising events and activities, and liaising with international young member groups from around the world. And I know we have the Rylam Youth Chair in the Asia Pacific region listening in today, who's also part of our CIA NEXGen steering committee, Liam Martin, who is based here in Sydney. A little bit of housekeeping before we start today. You'll note using Zoom that you have a menu bar that includes a Q&A button and a chat button. I'd ask that we use the Q&A button for any questions that you have for our speakers today. And if you could just include your name and affiliation, that would be fantastic. We'll ask the Q&A at the end of each of the presentations. So if you have a question after our first presenter today, or during that presentation, please put that in and I'll pause for questions at the end of that presentation, and then we'll do the same at the end of our second presentation. Please type the question when you think of it, otherwise the webinar might zoom on through and you might forget to put that question into the Q&A bar before the end of today's presentation. If you would like to have a little chat with myself or the presenters or the other delegates, please use the chat room. Don't put your questions in there though, please. Please use the Q&A, as that's what we're going to be using for that part of the webinar. Briefly mention our Platinum Company members. They are Leviat, Madewell Products, Wagstaff Piling and Cementate. All four of these organisations have been long-time members of the Concrete Institute of Australia and long-time supporters at a Platinum Company level, and we thank them very much for their support and their contribution. Once again, before we start our presentations, don't forget to use the Q&A button for any questions you might have for our speakers. And with that in mind, I will now introduce our first speaker for today. Our first speaker today is Shiwei Yu, who is a Senior Materials Engineer at Contour 3D. Let's get that presentation up. He earned his PhD in concrete 3D printing from Swinburne University of Technology in November 2022. Since joining Contour 3D, he's contributed to several landmark projects, including the Genesis, which is Australia's first full-scale 3D printed building, the Dubbo Social Housing Duplex, New South Wales's first 3D printed social housing, and the Block 2025 Cabana houses. He's currently developing Contour 3D's proprietary concrete mixes for diverse practical applications with a focus on driving innovation and advancing sustainability in the Australian concrete industry. I'm going to hand over control of my remote to Shiwei and allow him to get into the presentation. There we go.
Yeah, thanks for David for the introduction, and good afternoon, everyone. Thank you for the opportunity to present today. I'm very excited to share what we are doing in Sydney, and the topic of today's presentation is advancing low carbon construction through 3D concrete printing. My name is Shiwei Yu, and I'm a senior material engineer at Contour City based in Sydney. Okay, let's start it. First, let me give you a brief introduction of who we are and what we are doing. Some of you may already be familiar with us, but I'd like to do a simple overview of what we're doing. And at Contour 3D, we take a very different approach from traditional concrete construction. Instead of pouring concrete into the formwork, we use it as the ink to 3D print houses. So our team not only designed and build the printer in our warehouse, but also we develop the material ourselves in our lab. So beyond that, we also focus on creating standardized procedure to making the house in Australia. So first, what is 3D concrete printing? Broadly speaking, there are two main methods that are widely adopted in academia and industry today. The first method is extrusion-based concrete printing. This technique originates from the plastic printing, which is very common today. So instead of using plastic, we extrude concrete through a nozzle to build up the structure layer by layer. This is currently the most common method worldwide, and many of you may already see a lot of examples happening around the world. Here in Australia, we are now developing local projects to demonstrating the possibility of the 3D concrete printing. And the second method is the particle bed approach. So in this process, each layer of particles is spread evenly, and a binder is applied selectively to bind the specific area. So once the printing is done, the bound part can be extracted, resulting in a more detailed product. Well, this method has been explored overseas. It's come with significant limitation in scalability and on-site practicability. So which is make it very difficult to print on-site, but can be printed in the factory. And today's presentation is mostly about the extrusion-based concrete printing. And construction is a huge source of carbon emissions. About 38% of global carbon dioxide and cement alone make up around 8% of carbon dioxide. And traditional methods are really carbon heavy. They rely on cement, formwork, and lots of logistics. And here is the surprising part. The formwork itself can actually be more than half of the cost of the concrete construction. So concrete printing gives us a smarter option. Instead of wasting materials, we build layer by layer structures using only what's needed. That means less waste, less cost, and chance to create a lighter and more efficient designs. Plus, it's let us bring in recycled materials and low carbon binders much more easily. So in short, 3D printing is just a new tech. It's not just a new tech. It's really a pathway to low carbon construction. So when we talk about 3D concrete printing construction to low carbon outcome, the first biggest factor is the material efficiency. Because there's no formwork, we cut down heavily on timber, steel, and plastic waste. With layer by layer placement, we only use the amount of concrete that's actually needed. So no more over ordering just to be safe. And thanks to precise deposition, the material goes exactly where it should, which avoids unnecessary thickness and reduces waste even further. Altogether, this means less material, less waste, and much smaller carbon footprint. Another way of 3D concrete printing drives low carbon outcome is through optimized structural design. With this technology, we can print topology optimized and hollow structures that traditional method is very hard to achieve. This means we are able to reduce bulk material use by 20 to 60% compared to standard casting concrete. So on top of that, we can integrate cavities for insulation directly into the walls, which improves the overall energy efficiency of the building and reduces their operational carbon footprint over time. So it is not just about building differently, it's about designing smarter, lighter, and more sustainable structures. Another important contribution of 3D concrete printing is the ability to integrate sustainable materials. So in our mixes, we use a range of supplementary cementitious materials like fly ash, slag, calcium clay, and even recycled glass powder. This not only reduce cement demand, but also improve pumpability and help us control the cycling time. And on the printing side, we also recycle our own concrete waste, sending it to a local crushing stations to produce crusher dust, which we can then reuse it in our future jobs. This creates a local circular material loop. We have also tested lightweight aggregates such as expanded glass and recycled sand. These help lower the density of the concrete we use and reduce the embodied carbon dioxide. And finally, we use fibers to control the shrinkage and improve tensile stress. What's interesting is that because of the extrusion process, the fiber tends to align with the printing path, which can actually improve the performance compared to the traditional cast concrete. Then let me share a little bit about the sustainable material we are developing in Contour 3D. Our main product, ContourCrete, is a one-part ready-mix material by around 40% recycled content by volume. It has density around 2,050 kilogram per cubic meter, with excellent aesthetic quality, allowing us to create smooth curves and nice shapes. It's also tough and durable, designed for 100 plus years surface life, and achieve around 60 megapascal in 28 days. We have also been developing a lightweight mix, which called Feathercrete, which contain evenly higher recycled content by the recycled materials. And its target density is around 1,100 kilogram per cubic meter in 28 days. In 28 days is around 25 megapascal. But in the earliest testing we done in the factory, we can even achieve lower density, around 800 in our test. To support different project needs, so we supply our ContourCrete at different bags, like 25 kilogram bags for small applications and 1 ton bulk bag for the large scale construction jobs. Now let's look at the typical workflow for 3D concrete printing projects. It all begins with the architect and the structural engineer who creates a CAD file for the design. The file is then imported into a 3D modeling software, which generates a truth path. From there, the file is transferred to a 3D printer, which is translated into the machine language. Usually, it's kind of like a G code. At this stage, we can adjust the printing speed, pumping speed, and everything. From a material perspective, we still use the same raw ingredients as traditional cast concrete. But of course, reinforcement is essential as well, just like conventional construction, because concrete on its own is very brittle and it's very hard to control the quality. By combining this digital and material process, we are able to print complex shape directly without extra cost of formwork, opening the door to design more smartly. And when we look at the material for 3D concrete printing, what type of property we are looking for? The first one is the fresh state during the print. The first property is pumpability. The mix need to be flow easily through the hose and pump without segregation, bleeding, or causing excessive wear. This can vary depending on the projects. For example, in the factory, we might only use 10-meter hose, but on the large scale construction side, the hose length can be up to 100 meters. So the material has to be adapted to these different pumping conditions. The second property is the extrudability. The material must pass constantly through the nozzle and form stable filament without tearing or clogging. And the third is the buildability. Each printed layer has to be strong enough to support the weight of the layer above it. The part is interesting because on bigger projects, the lag time between each layers can be very long, up to 20 minutes. By then, the first layer has already gained some strength to support the upper layer. So for the bigger projects, maybe it's easier to control the buildability because we have more lag times. And next one is the open time, which is also the printability window. The material need to stay workable long enough for us to complete the printing, but then stiffen in quickly so the structure can hold its shape. So in practical, the time the material spent in the hose can range from 1 minute to 10 minutes. That's why open time has to be carefully adjusted for different projects. If you use a fast setting mix in your long hose, you can easily end up with a blockage. The next property is sextography or yield stress recovery. After the mix is sheared during the pumping process, it should quickly regain the stiffness to support the next layers. There's been a lot of academic research into this, but for large-scale construction printing, the effect is actually not that significant. That's because the lag time between the layers is usually very long enough to gain the strength instead of sextography. And finally, setting control. We need to manage hydration and early stiffening fast enough to keep the projects moving, but not that so fast that it may lead the cold joint between layers and pumping issues. This depends on many factors, the hose length, the lap length, ambient temperature, and more. The funny part is, if you ask me, can you print a house? I will say yes, it's very easy. But sometimes it's very hard to print a very small column, but very high, because we need to carefully control the setting time for that. Once the printing is done, the next focus is on the hardened property of the material. The first one is the early age strength. The mix must gain enough strength within a few hours to resist collapse, handling and environmental loss. To put this into perspective, on last projects, we might be placing more than 1 ton of concrete every hour. As the structure rises quickly, it also faces significant wind load, so achieving high early strength is very critical for us. The next one is the mechanical strength, just like the conventional concrete, the compressive, flexural, and tensile. Our current material typically reach 40 to 60 megapascal at 28 days, which is comparable to the structural grade concrete. And we also need strong interlayer bond strength, which I mentioned before. Each layer has to adhere well to the one below to avoid a cold joint. This is managed by carefully balancing the setting time and mix design. And when printing continues the next day, we often use mechanical method like the nails or chemical bond agents to connect the fresh layer with the thing we printed last day. Then there's shrinkage and cracking. Without proper control, plastic and drying shrinkage can cause deformation or cracks. Because 3D printing makes generally lack of coarse aggregates, so shrinkage control is very important for this mix. And finally, the durability. Just like traditional concrete, 3D printed construction must withstand weathering, carbonation, sulfur attack, and chloride penetration. So depend on different environment, we will design different material. One of the key concerns for the material performance is the 3D printed concrete is an isotropic of strength, which means the strength is different from different directions. This result come from the period when I do the PhD in Swinburne Uni. As you can see from this graph, printed structures show different strengths in different directions. The most obvious example is the direction 3, as you can see here. When we test flexural strength in this direction, the sample tends to fail by tearing along the interlayer bonding. As a result, the flexural strength and tensile strength here is significantly lower than others. This highlights the importance for architects and structural engineer for the design. So they need to be aware of this material behavior and tailor their design accordingly. To have a better understanding of the anisotropic behavior, we conduct void analysis using CT scanning and MIP test, then combine the result into a single graph. From the graph on the left, you can see the printed sample tends to have more small pores. The main reason is that 3D printed concrete doesn't go through the usual compacting and vibrating process, which in traditional casting helps eliminate the micropores. To address this, we use deformers in our mix to reduce the volume of the pores. The good news is that due to the high pumping pressure during the extrusion, actually it creates many of the pores out, so producing a denser microstructure. In fact, some researchers have even reported higher strength performance because of this effect. We also observe a distinct difference in void distribution between cast and printed samples. In cast concrete, pores are mostly round in shape, while in the printed concrete, pores are often elongated or directional, a result of the pumping of the extrusion process. So this difference in pores distribution is the main contributor to the strength and isotropic of the strength. So an isotropy doesn't just affect the strength, it's also impact the durability. We conducted durability tests in different directions of the samples, and here is one of the example, the chloride migration test. So in this case, the T2 direction, which is the side of the filament, shows a highest chloride migration coefficient. This means it is weakest direction in terms of the chloride resistance. The difference once again come back from the void structure. As I explained earlier, the printed concrete has a directional pores due to the pumping and extrusion process. And these make chloride ions migrate more easily in certain directions. So for designers, this adds more complexity to the design. So it's not enough to think about the mechanical strength alone. Durability and isotropy must be considered during the design stage. And next, what does it look like on a printing site? And it's not totally, but it's a lot of difference from the traditional construction site. And now we gain many of the experience, and I can show you a little bit from this presentation. First, there's a machine operator who controls the gantry movement. Our control system is wireless, so the operator can move freely around the site and make real-time adjustment. They monitor the filament quality and adjust the printing speed if needed. At the same time, they can see live data like temperature, pumping pressure, and more. The most important factor is the safety. So everybody on the site has access to the emergency stop, either through physical button or directly in the app. So sometimes mistake happens or unexpected events happens, and the safety is very important now. So everybody can stop the machine right away. Next, we have a material operator staying near the mixing and pumping unit. This person usually has a background in material science. The system run continuously mixing with the ready mix material, and the concrete is then pumped into the nozzle from a long distance hose. The, the key job is to adjust the water dosage depending on the material and the environment. And the water demand will change from time to time, but once the operator thinks we need to adjust the water dosage, change need to be made. And for this, we also run a 2.5-ton dry material silo, which feeds material into the mixer. The silo of the level of the silo need to be carefully monitored. When the level is low, another 1-ton bulk bag can be loaded in with a forklift on site. And also we have a dust collection system for the loading process because the dry material handling is very dusty on site. We care about the people's safety and making a green environment on site. And we must have a dust collection system for that. And here are some of the details we made on site. Firstly, just like traditional concrete, we always need reinforcement. For printed structures, we typically use longitudinal reinforcement along the filament path, as well as cross-sectional reinforcement to tie the wall together and ensure the structural integrity. Next, simple construction details like weep holes and termite preventions are actually much easier with concrete printing. Because the concrete is still in semi-solid state, we can simply cut it by hand when it's still fresh. So no drilling or no complicated formwork is needed. Of course, things don't always go according to the schedule. For example, here in this project, the drainage hole is collapsed with our printing path. So on site, our engineers made a quick decision to adjust the tooth path and create a new curve to accommodate the change. Since everything is digital and there's no formwork, this kind of modification comes at no extra cost. And in this case, it even add a unique architectural feature to the building. And just like conventional concrete, printed concrete is repairable. For example, when we cut out a door frame, one of the corner was damaged. To fix this, we used the same hand mix on site and did a bit sculptural patching to recreate the filament pattern. Now we have also developed custom hand tools to make these repairs easily and efficient. And we also develop our own mobile batch plant designed specifically for 3D concrete printing. Up until now, we have mostly relied on ready mix dry material in bulk bag, but this approach limits us because most of the raw material like sand or crushed dust arrive in wet state. So to use it in dry mix is very hard, and to dry this material is very carbon intensive. And now our new batch plant solve this. It has 4 separate silos, one for crushed dust, one for sand, one for cementitious materials, and one for the master batch, which is our additives and the fibers in our mix. So with this setup, we can adjust the ratio of each silo in real time, giving us more flexibility on site. And the heart of the system is a 100-liter pan mixer, which makes batch by batch. The most advanced feature here is the high accuracy moisture sensor. Water can be added in 2 stages, about 80% of the water at the start, and then the final adjustment is made slowly with the final water pump. This way, even if the sand or crushed dust has different moisture value, we can still achieve consistent mix quality in every batch. And let me show you a case study here. The first full-size 3D printed house in Australia we did. It was printed last year, received its occupation certificate earlier this year, and just sold earlier this month. This project is a duplex, and we use about 140 tons of dry material to print the ground floor, the ground floor walls. The upper floor is built with the traditional timber framing, which integrates seamlessly with our 3D printed structures. And if you look at closer, you will see the walls have many complex shapes, the kind that would be extremely difficult and expensive with traditional formwork. But with 3D printing, those changes come with no extra cost. The wall were designed as a double wall system with insulation poured into the cavity. The house got excellent thermal and acoustic performance, achieving 7.9 star energy rating. So in terms of cost, the construction cost will reduce by around 20 to 30%. Of course, it's hard to make a decision now because most of the cost is from R&D and machine development. But looking ahead, if we are scale up and printing more houses, I'm confident the cost saving will be even greater in the future. And we have now completed many projects across New South Wales and Victoria, and you will see more of our building appearing soon. If you are interested in details, you can find more detail on our website. One project worth mentioning is the social housing project. We work with the regional New South Wales. We finished this project in Double last year. Here, the 3D printing really showed its advantage because we can build faster with less labor. It's very practical way to help address the current housing crisis by developing more home quickly and cost effectively. Okay, here is a simple summary of what I present today. The construction industry faces a massive carbon challenge. Traditional methods drive up emission through heavy reliance on cement, extensive formwork, and material waste. That's why 3D concrete printing matters. It all offers a different method to reduce the carbon footprint here through greater use of recycled material, low carbon binders, and at Contour 3D, our contribution has been deliver integrated solutions, not just the printer machine, but also the low carbon material. These results help us use more than 50% of recycled content and addressing the critical performance concerns and make it happen. And looking ahead, by combining digital designs, sustainable material, and on-site printing, we believe 3D concrete printing will play a major role in delivering low-carbon, durable, and efficient construction on-site. Okay, thank you for attending this. And any problems?
That was terrific, Shiwei. Thank you. I'm going to take back control of the remote control. So if we do that one, back to me. Excellent stuff. Gee, that was a good presentation. Thank you. I was thoroughly engrossed by the work that you're doing there at Contour 3D. In particular, the mobile batching plant, I think, is just fantastic. Great innovation. And I can see that we've got a couple of questions in the chat room. I'll start with the first one, Shiwei, if you like. It's from Liam Martin from UTS. And Liam asks, a common issue for 3D printing is failure of the bottom layers during printing attributed to shear stress. Do you agree in this assessment, and how does this relate to the anisotropy of concrete material strength?
Thanks, Lillian, for this question. Actually, it's a very good question. So on the factory, this happens a lot. So when we print the next layer, the bottom layer is always the critical part. So it's the softest part of the whole print. But when we print on site, actually the house is very big for one layers, and the lap time for one layer is like 20 minutes of time. So when we print like the first 5 layer, is already 100 minutes for the first layer. So the buildability of the first layer, the bottom layer, is not that critical in this condition. But if we want to print something smaller, we need to find a very fast setting mix. So when we print the next layer, the first layer already gains some strength. But I agree, the bottom layer is the most critical part for the setting down control.
Question that was in the chat room. I know we said we weren't going to go there, but it's from Aaron Aranathayan. Is the 3D printed concrete from Contour 3D certified for structural use?
Yes. So we got a OC based on the masonry structure. So this is our 3D printed walls. But even we got certified, we still have the structure column inside our walls. So because it's the first structure, we still need extra protection for the walls. Yeah, that's how it works.
And one last question, another one from Liam. If the microstructure pore dimensions are different in 3D printed concrete, is the permeability and interconnected nature of pores substantially different? Does this affect durability concerns?
Yes, it does. I as a result, I show in the presentation, we did the like durability test in different directions. So it is different from direction to direction. The weakest direction is the side of the filament, and to better alleviate this behavior, we have collaborate with the painting companies to improve the penetration of different like chloride, sulfate attack to get the protection about our concrete.
Cool. All right. Well, Shiwei, thank you very much for a fascinating presentation. Some excellent questions as well from Aaron and Liam. If you'd like to chat with Shiwei during Sean's presentation, please use the chat room. Otherwise, please use the Q&A to ask your questions. If for whatever reason the Q&A button isn't working, then I will check the chat room when we finish Sean's presentation. But once again, thank you, Shiwei, for a fascinating look into what is happening at Contour 3D in the 3D concrete printing process.
Yeah, thank you, David, and thank you, Lam, for the question. Yeah, thank you so much for you
Good
guys.
stuff, mate.
Yeah.
All right, our next presentation is from Sean Alfred, and his presentation title is Leveraging Durability in the Design of Low Carbon Concrete. And as I get Sean's presentation up onto the screen, there we go. I'll just read out Sean's bio. Sean is recently started as a quality field engineer with Remedy Asset Protection in Melbourne, and he's a civil engineering professional with experience working in consultancy, contractor, and materials testing environments. Apart from engineering, Sean wears a graphic designer hat, which I'm going to, I think you'll enjoy during Sean's presentation, to explore different aspects of design, which keeps his creative mind developing. So, ladies and gentlemen, please welcome Sean to the microphone, and I'm just going to actually turn off my video and mute my microphone, and I'm going to give Sean control of the remote.
Oh, thanks for that introduction, David. Let me just see if I have control yet. Okay. Just want to double check to take care of that lag. I'm still yet to get any movement on the slides. Oh, there we go. All right. Thanks again for your introduction, David. and it's a pleasure for me to be here. Good afternoon, everyone, and thank you for having me. I'm excited to discuss this topic, which I think is increasingly shaping how we design and build with concrete. And that is to move towards performance-based durability designed to reduce carbon emissions from concrete. This presentation will cover the items that you see on the overview list here. And what we'll basically do is explore how shifting our focus from prescriptive requirements to performance targets can lead to more durable and sustainable outcomes, aligning with engineering goals and climate objectives. By the time or the end of this presentation, about 95,000 tons of concrete will be produced, and that will equate to about a release of 85,000 tons of carbon into the atmosphere. The chemical and thermal combustion process involved in the production of cement is a major source of most of the carbon emissions that we get from concrete, with 60% of which are direct emissions from the heating of limestone, which produces the clinker, and 40% coming from the combustion of fuels that are used in the cement kilns. And concrete production accounts for about 8% of global carbon dioxide emissions. And it is expected that there will be a 23% growth in the consumption of concrete by 2050 in developing economies, while developed nations face a massive need for infrastructure renewals. Now, this means that the reduction of global carbon emissions from concrete is an imperative action that we need to take to realize sustainability goals and actually positively impact the environment. Let's see if it's a bit stuck again. You can see here in this chart for the projected net zero pathway, which was drafted by Global Cement and Concrete Association, that the biggest threat and the benefits to achieving that goal of reducing carbon emission heavily depends on actions involving how we design and construct with concrete. Particularly, you see the percentages up there from the efficiency in design and construction, the efficiency in the concrete production, and savings from the materials or the binders that we're using within our concrete. So what exactly are we talking about when we say low carbon concrete, and how do we achieve such concrete given the current landscape of concrete production? We can basically say low carbon concrete is concrete with significantly reduced embodied carbon, which encompasses all emissions of the entire life cycle of the material, compared to, for example, the conventional Portland cement concrete. But this isn't just one aspect, and it's a family of approaches that all feed into the emissions that come from the material itself. Now, the primary strategies include cement replacement using supplementary cementitious materials and alternative binders like alkali activated materials or calcium sulfur aluminate systems. With mix optimization, the idea is to reduce cement content through improved particle packing and enhanced performance additives. Now, increasingly, we're seeing as well carbon utilization technologies that actually capture carbon dioxide and use it within the concrete production as a way of reducing the emissions. Now, within this presentation, I will not delve too much into this last point, but discuss more on the cement replacement and the mix optimization approaches. So in the context of low carbon concrete, durability essentially is sustainability. And durability matters now more than ever. And the more we can extend the service life of the concrete structure, the more we can write off the embodied carbon from the manufacturer's transportation and installation of construction materials over longer periods. And traditional specifications call for fixed cement content and typically 350 to 450 kilograms per cubic meter. Standard water cement ratios between 0.4 and 0.55, and limited SCMs or supplementary cementitious material percentages, usually no more than 30%. Now, this one-size-fits-all approach usually results in 20 to 40% over specification in certain instances of cement content, creating limited optimization opportunities, and it also presents barriers to innovation in binder systems that can be applied, and often overlooks the actual exposure conditions where the concrete structure will be in. Now, the performance approach uses measurable performance indicators, for example, permeability coefficients, that quantify transport properties through the concrete, chloride diffusion rates that predict service life, and carbonation resistance that can ensure steel protection, and service life predictions based on actual exposure conditions. In essence, what you have is prescriptive design tells us how to build with rigid specifications that restrict alternatives and limit optimization, whilst performance-based approaches pretty much tell us what to achieve with the outcome-focused flexibility that encourages innovation and enables extensive optimization opportunities. Now, durability, as we said, is quite essential, and not just to prevent the degradation of the concrete, but to reduce the life cycle emissions. And a structure that lasts twice as long requires fewer repairs and fewer replacements and has lower total carbon footprint. So the goal here is to actually design concrete that not only performs on day one, but continues to meet functional and structural requirements over decades. In the world of concrete durability, there are performance tests, like I mentioned, from the durability indicators, or what we call performance tests, that are employed to assess various characteristics of the concrete with respect to its resistance against deterioration mechanisms. And, chief among these are chloride and carbon-induced deterioration. Now, tests for permeability, chloride ingress, and carbon resistance give an indication of the ease with which we can anticipate degradation or deleterious materials to penetrate the concrete, which then affects the deterioration, particularly the reinforcement. And you can see here some respective values that I have added that would qualify as acceptable good durability performance or indicators with respect to either permeability or diffusion or carbon coefficients. The values that we get here from these tests can actually be used as input parameters in service life models to predict what the actual performance over time may be with respect to a specific exposure environment. And this in turn gives us that confidence to optimize concrete mixtures for both performance and carbon reduction. Now we'll take a look at some alternative binders that offer a way to designing low carbon concrete mixes, which exhibit favorable durability performance characteristics. Now, beyond just a Portland cement or general purpose cement, I'll specifically focus on alkali activated materials, which are a class of inorganic binders that are produced by reacting an aluminosilicate source material with a highly alkaline solution. And the source material is typically an industrial byproduct or natural material rich in non-crystalline or semi-crystalline aluminum and silicon. For example, fly ash, ground granulated blast furnace slag, metakaolin, and other materials like rice husk ashes and mine tailings. Now, the key characteristics that make these AAMs a solution to designing low carbon concrete is actually twofold. On one, you have the environmental benefits and the durability characteristics. So AAMs offer a cleaner replacement for cement-free concrete in that they utilize industrial waste products, translating up to a 70 or 80% carbon reduction potential. And you may ask how this is possible. And now to do this, I'm going to use calcium clay LC3 as an example. Right, so LC3 contributes to the reduction of carbon emissions mainly by substituting the energy-intensive clinker content And one innovation, using this example I've put on the screen, is to use 50% of the clinker content from normal OPC with 30% low-grade kaolinite clay, 15% limestone, and 5% gypsum. And what that does is the lower use of the clinker content reduces the carbon emissions released during production processes by up to 40% compared to ordinary Portland cement. And this is because in the production of the calcium clays, they're more malleable and heated at about half the temperature as you would in normal clinker production of ordinary Portland cement. Now, in terms of the performance characteristics or the durability aspect, AAMs possess reduced permeability and increased resistance to aggressive environments. And a denser concrete microstructure can be formed from the poor refinement of using these materials, significantly decreasing the permeability of the concrete to penetrative substances, chloride, iron, sulfates, and other aggressive chemicals. As a side note, although I didn't dive so much into them, when you look at either like calcium sulfur aluminate cement, these derive their strength from the formation of ettringite, which is like a needle crystal formations, and those offer like a more conservative alternative with performance comparable to OPC systems for permeability and enhanced chloride resistance due to the ettringite formation and moderate carbonation resistance. So they're not as powerful as you'd get, or the benefits that you would get from AAMs. And existing research work also indicates that these alternative binder systems exhibit a high resistance to chloride ion penetration and the characteristics that we look for, like using high SCM replacement levels. But to date, you find that there's still caution to use high percentage replacement of SCMs because there's limited field data to assess whether observations from accelerated tests are comparable with actual field conditions. Now, if we look at trying to optimize our concrete designs from the mixed constituents themselves, optimizing concrete mix design to reduce emissions focuses more on balancing the performance with that sustainability aspect. And as we saw earlier, cement production is the most carbon intensive component within the concrete, and the supplementary cementitious materials that we have shown here actually help to lower that cement content by thereby cutting the carbon emissions. Now, using recycled aggregates is also another way, and all the alternative binders such as geopolymer cement can further reduce the reliance on resource-intensive Portland cement use, and improved water cement ratios and chemical admixtures can help enhance strength and workability, thereby minimizing waste to achieve the mechanical and durability properties that we need given a specific environment. Now, key to the mix design optimization is understanding the exposure conditions the structure will be in service versus the material constituents that can be put together or make up a mix that will meet the design service life targets, for example. As you can see, it's more than just workshopping the black box specifications or prescriptive specifications that we are used to seeing it in most standards and prevalent construction practices. And what we're also seeing that is advanced modeling and testing can ensure optimal durability performance mixes with reduced carbon impact. I'm going to show you an illustration of how that might look like using a 4-stage framework. And this might appear as like a complex level using data analysis and machine learning. So what you have here in this flow diagram, it's taken from a study to enhance concrete mix designs for precast concrete segments for a tunnel. This was actually done in China. And what you see is the data is acquired from tests, and that is from mechanical properties or durability indicator parameters, which are then processed and optimized using algorithms to model the best solution. In this case, that would be the mixed proportions for the concrete design. And the generated algorithm is verified through comparative analysis and microscopic testing of the concrete microstructure. Now, I'm sure you'll agree at this level, to realize the true potential of such an approach or strategy to low carbon mix designs, this requires a lot of rigorous testing and research development. And this brings us to the next point of our discussion, which is the challenges and approaches to designing low carbon concrete. So I've kind of grouped these into like 4 items to specifically discuss this. And durability and performance considerations are critical. We've established that they're critical in evaluating low carbon concrete alternatives, especially in light of increasing environmental concerns and the need for sustainable concrete material, construction materials. But with any transformative change and wide acceptance to these approaches, the challenges are already there, and there's always some hesitation to adopting these strategies beyond the laboratory environment. Now, I've grouped these into 4 items, which are material variability or availability, durability mechanisms, knowledge gaps that exist, and regulatory or market hindrances. Now, if we look at materials availability, currently we have about 300 million tons per year of traditional SEMs that are available globally. And when I say traditional SEMs, I'm talking about your fly ashes, your slags, those industry byproducts. But to achieve a 50% cement replacement across the industry within our normal concrete production, we're going to need about 1.5 billion tons per year. So you can look at already the mismatch and the gap that's there with available SEMs stocks versus what we actually need if we were to change the way we design our concrete across the board. And further substitution and replacement depend on locally available materials. For example, in Europe, there's limited availability of fly ash and slag, and there's already a push toward alternative systems incorporating limestone and metakaolin. And here in Australia, we have limestone, slag, and fly ash, which are prevalent SEMs that are used within industry. And you already know with the fly ash and for example, in the near future, we're going to expect that the coal is going to be phased out. And so the supply of this fly ash, and as well as slag from the amount of steel production that's there, these availabilities might change over time. And so we start to see that natural pozzolans or materials are underutilized, and calcined clays, like I've given an example of, actually have a tremendous potential to meet the needs of the changes and enhancement in the way we design concrete is going to be. And of course, the solution will look different in different parts of the world based on the regional material availability. If we look at the aspect of the durability mechanisms, we see that the studies have shown that SCMs like fly ash and slag can enhance durability performance, but this enhancement actually relies a lot on the proportions that are used and the specific environmental conditions. And what is critical to understand here is that the difference in the chemistry of these materials means different rules. For example, if I take a higher SCM content, it can enhance the chloride binding, which can contribute, of course, to the corrosion resistance, particularly for high alumina contents, SCMs like GGBS and metakaolin. But on the other hand, SCMs like fly ash and silica fume do not necessarily have as high an alumina content, but improve the pore structure of the concrete, thereby reducing the permeability. And the challenge that we have is some of these SCMs have low pH which then encourages or like translates to higher carbonation rates compared to OPC. But then the pore refinement reduces transportation rates. Now, in this case, the considerations can actually be made of using surface treatments, which may be a value add to the durability performance of these materials if we do decide to use them. And so we can therefore say that different durability indicator methods are required to gain better understanding of the durability characteristics that you would get from using different either mixed proportions of the SEMs that are included in the concrete mix designs tied to a specific environmental or exposure condition. Now, if you look at the knowledge gap, a lot of gaps exist in understanding the performance of most of these alternative binder systems, particularly the lack of real world exposure data. And most research and analysis relies a lot on accelerated tests, which limit the correlation with the actual long-term field performance. There's still room for development, of course, for service life models that are calibrated for alternative binders and alternative binder systems, which and these limitations actually then necessitate rigorous testing and analysis for probabilistic data for alternative binder systems to be able to scale to a wider acceptance of these carbon reduction strategies in concrete design. If we then look now at the regulatory and market barriers, what we see is that adoption of performance-based approaches in concrete design is currently fragmented. Why I say that is if we look at our existing Australian standards and local codes, we see that most of the use of alternative binder systems like SCMs is usually left to a decision that's up upon the specifier or the asset owner, for example, in aggressive environments. And state guidelines and durability series, which actually exist here, allow durability indicator tests to be specified for durability assessments. I can give an example of maybe Transport New South Wales or even Vic Roads, which specify durability tests to be done as a way to assure the quality of the concrete to meet the exposure needs and the service life. And this shows a positive step towards performance-based concrete design. However, full adoption is yet to be implemented, and for wider acceptance, you would expect that at some point, the standards that we see from, for example, the concrete AS3, the 3600 and AS 5100, to fully adopt this across maybe the whole of Australia, there needs to be a pioneering or a movement from them to update these designs to accommodate such strategies. And likewise, on an international scale, the standards adopt performance-based approaches to varying extents. And this already highlights the lack of harmonization of testing protocols and approaches. But it does give that opportunity then to have further development and analysis of testing approaches that can improve our knowledge and confidence in these approaches. And lastly, the adoption of non-conventional concrete design is yet to be associated with higher systems in terms of service life extension and sustainability. And when you look at the costs that are involved initially into using alternative binder systems, there's that hesitation to want to go down that route, but with often overlooking the benefit that comes from, for example, what the maintenance schedule of such a structure would then be over time versus when you use normal ordinary Portland cement. And to close off, prescriptive specifications, we've seen that they limit our ability to innovate and reduce the carbon impact that comes from our concrete designs. And performance-based design approaches actually enable us to use alternative materials effectively to optimize our mixes and to design for longer life with low environmental impact. And adoption challenges such as the technical barriers which we've discussed and regulatory limitations often necessitate for us to have more research and development around these materials to gain that wider acceptance. And I think key to this is understanding that there needs to be increased collaboration between academia and industry to drive this wider acceptance and confidence in using alternative or green concepts within concrete design to meet the durability and environmental needs within the concrete industry. And with that, I say thank you for your attention, and I welcome any questions. If you need to connect with me, I've just left my details there for my email address and my LinkedIn. I'd love to connect and chat more.
That was terrific, Sean. Thank you very much. I could not agree more with just about every point you made there, particularly at the end. I, for one, have had lots of discussions over the years about prescription-based specification versus performance-based specification, and it's terrific to see our young professionals really honing in on the importance of performance-based requirements, particularly as we are moving into some uncharted territory when it comes to concrete design and specification. And as I said, I couldn't agree more with you on all of those remarks, and also around the barriers. And it was a discussion that we had in depth at our conference last week in Adelaide. And there are a number of barriers, but a lot of them do revolve around the adoption of new materials. Why is there a resistance to do that? Because there's no real benchmark or standards. Why is there no real benchmark or standards? Because there's a resistance to performance-based specification. Yeah. So it all sort of revolves around. Okay, I can see that we've got a few questions in the Q&A, and so I will start with the first one, which is from Gunja Shah. And they've asked, what would be the best method or test to predict the service life of concrete when we're looking at low carbon concrete?
Well, I think it all boils down to ideally where the environment in which your concrete is going to be in. There's so many different service life models that exist to predict a performance. The drawback is just that if I look at locally, there's not that much. When you look at, for example, if you take it to the very, very start, when we're still trialing mixes that we want to use for a particular structure, most of the qualifying metrics that we use is, can we achieve the strength? Are we going to have the strength that we need for the structure at the end of 28 days? And that's usually what qualifies to say, okay, this is what's going to happen. If we look at other tests like strains and shrinkages and how they mix, they're limited, and you don't necessarily find so much about testing using durability indicators. For example, gas permeability, or to see or to use accelerated tests at the very beginning to sort of project where or how that material is going to perform, or a certain mix is going to perform. So I feel the best method and approach to take is to collectively think about the environment that the concrete is going to be in, and what different effects, or understanding the deterioration mechanisms of that environment, and what best to use or to add within your concrete to counteract or to resist those further. And it all starts from how you are building up that mix design from that trial mix in a laboratory environment, and also trying to see. I have. From my experience working in a South African environment, they have a gas permeability test that they do to qualify, because there's a lot of hesitation when you just look at a laboratory environment test, because it doesn't necessarily reflect what happens out in the real world. You can only believe the test results so much. So some of the testing or developments that we're seeing is you run parallel tests from the laboratory and out in the actual field, where you have mock panels that are also tested after 28 days to see that what we've designed for in terms of durability is actually is actually according to what we've seen in the laboratory environment, and how that can then be qualified. So I think it all starts from the development of the mix design itself to be able to predict the service life, and actually accommodating service life models and engaging durability consultants to plan how you want your structure or your asset to be within its designed service life.
Question from Liam Martin. The use of alkali activated materials and geopolymers often require fly ash and slag as a base material. With expected shortages in these materials in the future, does this not limit the impact of AAMs to reduce future carbon?
Thanks for your question, Liam. I totally agree. It does limit the future outlook of whether there's even any need for us to be considering such materials if they're going to be depleted in any way. But if we do then look at, for example, even other constituents within our mixed designs, if we're looking at the sand or your coarse aggregates, there's a lot of issues or a lot of concerns around resource depletion. And so I think it actually gives us that opportunity to think innovatively and not just using that black box structure to say, as long as we have this one particular material, this is how we're going to achieve the mechanical or durability characteristics that we need. I think it should encourage then more a vigorous or rigorous testing and research and development to figure out what other alternative materials can be beneficial and give us a positive environmental impact as well. So I think outside the concern of the materials possibly depleting, there's opportunity for us to explore other alternatives. And I definitely see with the way things are going within industry, adoption is the biggest challenge that we have. But I believe there's a lot of research going around of alternative systems that can be applicable to meet that.
And I think we can learn from other countries as well with
Certainly.
that in mind, because not all countries have the same level of accessibility and the amount of resource when it comes to particular types of SCMs. In fact, we just look over the ditch to New Zealand, and they definitely have issues around supply in SCMs, and so they are looking at low carbon concrete and the race to net zero through a different lens. So there's lots of different ways we can learn from different countries. Question from Dinesh Mahanama. One challenge associated with the use of byproducts such as fly ash and slag is maintaining consistent quality control and assurance. Variability in these materials can lead to undetected durability or operational issues. What would be the most effective approach to mitigate this risk?
And I think that's a very good question, Dinesh. And I think a lot of it actually boils down to how we enforce our construction practices and how we look at the aspect of quality control and quality assurance. I believe in the industry right now, this still lacks greatly, because if we look at a laboratory environment, a lot of the conditions that are within that space are controlled. So if we want to achieve a certain result, we're pretty confident we can do that from a laboratory environment. But if we do take that mix that we say we're going to use to build a certain structure and put it out in the field, you're looking at there are different variables that are now involved. The construction quality, the experience that comes in making sure that this is the way that they're going to construct a certain structure, and how do we make sure that same quality or characteristics that we've seen from laboratory tests is achieved on site. And a lot of that boils down to the quality aspect of it. And this is where we sort of come in as durability consultants. And it's just that it's not enforced within industry at the moment, but there's a need for having a step where there's that quality assurance stage. Initially, for example, when we qualify the strength of your concrete after 20 days, if it meets a certain strength, then that's okay. But then there's also a call for need to have field tests of durability indicators that can tell you whether specific targets have been met. Some of the standards that are there currently in terms of durability do already specify like benchmarks or target values with regarding to your chloride migration or your gas or water permeability. So if we can have tests that are there to actually assess the durability characteristics or performance of the concrete at the point where it's initially constructed, it can help us to then in meet or mitigate the risk that you're worried about the quality and the variability. Then if we go back to the material itself, like you said, the source of where the material is coming from is going to vary a lot. Is there a way that we can benchmark the quality of such materials to say this is at an acceptable level or this is not? So I think it's a lot of it comes from driving how we're going to if I can put it like policies or standards of practice that we can put across to make sure that it all becomes consistent. And that's quite a bit of an effort and a challenge that exists because there's a lot of disharmony in trying to put that together.
That's a terrific answer, Sean. Two more questions before we wrap up today's webinar. Another question from Liam. One of the main barriers to adopting new technologies is in the degree of risk for the asset owner and manager. Do you see changes in these procedures via standards and specifications happening in the future that relate to alternative binders and designs, taking LC3 systems or performance-based design as examples?
I certainly think there will be change. It's just the question. I think the question that we'd rather be asking ourselves is, will it happen at the pace that the world needs it at the moment? Because I do believe there is existing knowledge, there is research going around it. The implementation rather slow than we would want it to be, put out there and actually standardized. So that's where the biggest challenge is. How can we get a faster way of standardizing these ideas and innovations to a point where they're widely accepted? You would be surprised at the number of projects where the asset owner and the designers are actually adopting or using these alternative binder systems. I can make an example of the Sydney Metro tunnel. They've used alternative binder systems in there, and the success, of course, of some of these let me not say these leaps of faith to believe in these materials will of course be seen maybe at like 50 years later when the material when the concrete is actually in service, whether it's meeting the specific needs it was designed for. So I do believe there will be change over time. Whether or not it's going to be as fast as we want it to be, that's another question.
Absolutely agree. And there's also the incentivization for asset owners and managers to take that risk. That also comes into play. And at the moment, I'm not sure that we have enough incentive in place for that to happen on a more regular basis. Last question is from Eddie Huang over in South Australia. SCM's lower calcium hydroxide but refined pore structure, is reduced permeability enough to maintain carbonation resistance? And how do we control SCM dosage? And what current strategies are used to tackle this issue in practice?
Yeah, that's a very good question, Eddie. I for the first part of your question, I honestly think it boils down to understanding the exposure environment, and a lot of it considering if we look at the aspect of the probabilistic analysis. If we're worried about the use of our SCM and the increased carbonation rates, for example, does that outweigh the severity or the level in which carbonation actually, the carbonation environment around it, whether it's going to actually degrade the concrete at a level that is alarming, or what mitigating factors can we put in so that it can be slowed down? It's about outweighing the benefits versus the risks. If you're going to use your OPC instead of using the SCM, where does that leave you after 25 years in terms of your maintenance schedules versus if you're going to adopt using the SCM at the same service life. If we do then think about the second part of your question, I might have blanked out a little bit there. If you could just bring that back, David.
I will do that. Hang on a sec. Where are we? Down the bottom there. There we go. So how do we control SCM dosage and what current strategies are used to tackle this issue in practice?
I think in practice might be more of a challenge. A lot of the insight that should come from there is from more research and a lot. See, I think one of the challenges that's there is because we can't. When you have accelerated tests from a laboratory environment, they give you an indication of how the material is going to behave, but if you look at the essence of climate change and how our temperatures are changing over time and exposure environments, can we actually say these accelerated tests give us a clear indication of what will happen in reality? That's still a question that remains to be answered. But I do believe a lot of the insights still should rely a lot on research and development at the moment, and outside of it being confined to an environment, a laboratory environment, there need to be trial tests actually being ongoing trial tests in the field that are running right now to build onto the confidence that we're getting from the information you do from your research. I believe that's the only way we can increase the confidence in knowing how much of SCM we can actually apply. What are the limits? What risks are involved with increasing the content and etc. So research and development is how I can simply put it.
Fantastic. I think we'll leave our questions there, but I would like to thank both our speakers today, Shiwei and Sean, for two fantastic presentations. I've thoroughly enjoyed both of them, gents, and I do appreciate not just your time today, but the time and effort you've put into both those presentations. They were detailed, but they were extremely informative, and I certainly learned a lot from both of your presentations today. So thank you very much on behalf of all our delegates. Before we wrap up today, just a couple of things. As always, we have a number of professional development opportunities through the Concrete Institute of Australia. We've got webinars like today, and today's presentation was also recorded. And once we've tidied up and edited the recording, we'll also make today's presentations available through our YouTube page for anyone who wishes to view them. We also run a number of technical seminars around the country, and it's best to check our website to see where the next seminar is in your part of the country. And we have a bunch of recorded on-demand materials available as well, including all the webinars that we've run over the last number of years. And speaking of webinars, our next webinar is on Tremie Concrete coming up next Thursday. The title is Guidance on Tremie Concrete for Deep Foundations, Good Industry Practice Update. And that'll be presented by Dr. Martin Larish, who's been heavily involved in the geotechnical and piling sector of the concrete industry now for a number of years. Martin is currently based over in New Zealand, but has had extensive experience over here in Australia and was also heavily involved in the development of the Tremie Concrete Recommended Practice put out by the Concrete Institute of Australia. So very much worthwhile tuning into the Tremie Concrete webinar next week. And with that in mind, I thank all of you for attending this afternoon. Once again, thank you to our presenters. Thank you to Arun and Sachi for organising today's event on behalf of NEXGen, and we hope to see you at our next event soon. Thanks very much.